The process of star formation is a cornerstone of astrophysics, as it explains the origin of stars, the primary building blocks of galaxies. A pivotal concept in understanding star formation is the Jeans Instability, a theoretical framework that describes how interstellar gas clouds collapse under their own gravity to form stars. Named after Sir James Jeans, who first articulated the principles in the early 20th century, the Jeans Instability Criterion plays a fundamental role in elucidating the complex interplay between gravity, pressure, and thermodynamics within molecular clouds. This document provides a comprehensive exploration of the Jeans instability and its relevance to star formation. The discussion encompasses the physical conditions for instability, mathematical derivation of the Jeans criterion, observational evidence, and the subsequent stages of star formation. Star formation begins within the interstellar medium, ISM, a vast, tenuous collection of gas, dust, and plasma that permeates galaxies. Within the ISM, regions of higher density, known as molecular clouds, serve as stellar nurseries. These clouds primarily consist of molecular hydrogen, H2, along with traces of helium and heavier elements. Molecular clouds are characterized by densities typically around 10 superscript 2 to 10 particles per cubic centimeter, temperatures ranging from 10 to 100 Kelvin, which allows for the formation of molecular hydrogen, masses spanning from a few solar masses, m, to several million m, and sizes from a few parsecs to over 100 parsecs in diameter. These conditions make molecular clouds susceptible to gravitational collapse if the internal support mechanisms, such as thermal pressure, turbulence, and magnetic fields, fail to counteract gravity. This sets the stage for Jeans instability. The Jeans criterion determines whether a region within a molecular cloud will collapse under its own gravity. The concept balances two opposing forces: the inward pull trying to collapse the cloud and the outward push resisting the collapse, arising from the random motion of particles. The Jeans length is the critical size scale above which gravitational forces dominate over thermal pressure, leading to collapse. The Jeans criterion predicts that a molecular cloud will collapse if certain conditions are met. Factors influencing these conditions include temperature, where higher temperatures increase thermal pressure, stabilizing the cloud; density, where higher densities favor gravitational collapse by reducing the Jeans length; turbulence and magnetic fields, which can provide additional support against collapse; and external pressures, where interactions with supernova shocks or spiral density waves can compress clouds, triggering instability. Modern astrophysical observations provide compelling evidence for Jeans instability and its role in star formation. Observations reveal that molecular clouds often fragment into smaller, denser cores before collapsing. These cores correspond to regions where local conditions exceed the Jeans criterion. Infrared observations detect protostars embedded within collapsing cores. These young stellar objects represent early stages of star formation initiated by Jeans instability. Many stars form in clusters, reflecting the fragmentation of a single molecular cloud into multiple Jeans unstable regions. The collapse of a Jeans unstable region follows a sequence of stages, leading to the birth of a star. Once the Jeans criterion is met, the region collapses under gravity. The density increases, and the collapse accelerates. As the core becomes denser, it heats up due to the conversion of gravitational energy into thermal energy, forming a protostar at the center. Material from the surrounding envelope accretes onto the protostar, further increasing its mass and temperature. When the core temperature reaches approximately 10 million Kelvin, hydrogen fusion ignites, marking the transition to a main sequence star. While the Jeans instability provides a foundational understanding of star formation, additional factors influence the process. Magnetic forces can delay or prevent collapse by providing additional support, but ambipolar diffusion allows gravity to eventually dominate. Supersonic turbulence within molecular clouds can create localized regions of high density, promoting collapse. Phenomena such as supernova explosions, galactic collisions, or spiral density waves can compress molecular clouds, initiating star formation. The Jeans instability and subsequent star formation play a critical role in shaping galaxies. Stars synthesize heavier elements, enriching the interstellar medium through supernova explosions. Young, Massive stars produce stellar winds and radiation, influencing subsequent star formation. Star formation contributes to the structural evolution of galaxies, including spiral arms and starburst regions. The Jeans Instability remains a cornerstone of our understanding of star formation. By identifying the conditions under which gravitational forces overcome thermal pressure, the Jeans Criterion provides a robust framework for studying the birth of stars. While additional factors such as turbulence, magnetic fields, and external triggers add complexity, the fundamental principles outlined by Sir James Jeans continue to guide astrophysical research. Observational advancements and computational simulations will undoubtedly refine our understanding, shedding further light on this fascinating process.